All right. So one of the things that we've talked about, and we will still talk about constantly as we go and make it more sophisticated, is the concept of biasing. How do you generate the bias voltages? How do you keep the transistor biased? So we'll start talking about that right now, and then we'll expand on it as we go. Later on, we'll talk more in depth about supply and temperature independent biasing. We talk about band gaps, p-tats, c-tats later on. But right now, the first question is that what are the general qualities of an ideal bias? And then let's compare some basic biasing techniques. So let me ask you this question. If you're trying to generate these voltages to kind of bias your circuit in a certain operation point and put it in there, what are some of these properties of these voltages and currents that you're trying to generate? Let's say these current sources, voltage sources that you're trying to generate. What are some of the fundamental properties of those that you would like to have? Well, you want them to be not particularly dependent on temperature. You don't want them to be varying too much with the parameters of the process if the transistor parameters changes. You don't want it to change. For example, in a bipolar transistor, you don't want it to be dependent strongly on beta. In a MOSFET, you don't want it to be strongly dependent on mu and C aux. You don't want it, and then you don't want it also to be dependent on supply voltages, for example, to the extent that you can, right? I mean, you don't want it to be something that if your battery is charged, behaves very differently from the time that your battery is empty. So if you're trying to make circuits like that, you want to make it as robust in that sense. So let's start with some very basic things. I mean, if you think about, for example, a BJT, a bipolar transistor, and some sort of a common emitter stage. So let's say you have an RC. So you have a VCC. So if we actually try to bias it like this, some sort of a fixed VBE here, what is the problem, or is there any problem with this? Well, first of all, you know that this current IC is going to be has an exponential dependence on this VBE. So small fluctuations or variations of this will translate to large amounts of changes in the collector current, right? Which basically is how you're getting gain anyway out of this thing. It's that exponential behavior that you're exploiting to get gain. So this doesn't appear to be a very good way because it's very sensitive. Now, and the other thing is that you really don't have ideal voltage sources anyway to begin with. So how do we do that? So let's say you have a power supply and you want to generate it off of this. So the next step would be to to have something like this. If you have a resistor, a base resistor, let's say, a second resistor that connects it, and a collector here. So now these are, as we will see, initially at least, this set of biasing techniques that we'll be talking about are more conducive to discrete circuit design. And you'll see that how it will lead to a discrete example of these amplifiers. And then we'll see how to go, when you go to integrated variations, how they will look very different. So if we do something like this, what are the voltages and currents going to be? So how can we calculate what the collector voltage of this, collector current of this thing, for example, would be? Do we know how to calculate it? Well, it's really determined by the base here. The base current, IB, is determined by the difference between VCC and some VBE on, right? On voltage. Now, why do we talk about VBE on? We know it's an exponential dependence, right? Why do we treat it sometimes like a fixed 0.7 volt or something like that, 0.6 volt, 0.7 volts? Why do we do that? Why can we do that? Well, the reason really goes back to that logarithm here. So let's pick an example. Let's pick a numerical example for you guys to see. So let's say your IS is 10 to the negative 15 amps. Just some saturation current number, right? If that's the value, let's say at 1 milliamp of current. So let's say your IC is 1 milliamp. What is VBE? Well, VBE is going to be VT natural log of IC over IS, which is going to be VT natural log of 10 to the minus 3 divided by 10 to the 15, so that's 10 to the 12. Okay? Which is basically 12 VT natural log of 10. Okay? And VT is 25 millivolts, right? So that's basically 250 plus another 50, so that's like roughly 300 millivolts, 0.3 volts times natural log of 10. And natural log of 10 is whatever, 2.3? Yeah, 2.3. So that times 0.3 So that's 2.3. So that's roughly 0.69 volts. That's where that 0.7 really comes from. You may say, well, but if I'm not operating at 1 milliamp? What if I'm operating at 10 milliamps? Well, if you're operating at 10 milliamps, all of this would be the same. This would be 10 to the 13, right? So this, you add a 25 times 2.3 to this whole thing. You add 57 millivolts to it, right? You can do the number directly, but this becomes essentially, instead of 12, this becomes 13. Right? Let's do it this way. Let's actually calculate this number. So it's 25 times natural log of 10. This is 57 millivolts. Right? So if I go from 1 milliamp to 10 milliamp, this factor instead of 12 would be 13. So I go up by a factor of 57 millivolts. And if I go from 1 milliamp to 100 microamps, this is going to go down by the same factor. So I'm going up and down 60 millivolts per order of magnitude. So as long as I'm in that order of magnitude, I mean within a couple orders of magnitude of that, I'm within 60 millivolts, 100 millivolts of that. So that voltage is going to be in the range of 0.6 to 0.8 for typical currents. Now, if you're operating at like 1 nanoamp, then that voltage is going to be very different. Right? So there's nothing magical about that. It's an artifact of the value of IS you get, which also has relationship to band gap of the semiconductor and things of that sort, as we'll see later when we talk about temperature-independent biasing and things of that sort. But that's what it is, right? But therefore, assuming that this VBE on is roughly around 0.7 volts is not a horrible thing. But you have to understand where it comes from. Nothing magical there, right? Because it doesn't change that much because of the logarithm. So now let's go back to this thing. If this is 0.7 volt, this is, let's say, 5 volts. So whatever it is, right? I mean, so let's call it, what is this current? That current, IB, is going to be VCC minus VBE on 0.7 volts divided by RB. So that determines my IB. So it seems that IB is reasonably defined. I mean, yes, it's related to the VCC, and it's determined by a resistor, but it doesn't have this like horrible exponential dependence. But the problem is that the current that you really care about is IC, which is beta IB. So it has a beta dependence. And for a bipolar transistor, beta is really not the parameter you want to be counting on. Because we saw it was basically what? Alpha over 1 over alpha, 1 minus alpha, right? It's a ratio of something divided by 1 minus number close to 1. That number fluctuates a little bit. That ratio changes a lot. So it is very sensitive. So this is not really the best way of defining this. So how can we improve this? Starting from this, going to the next step. How can we improve this biasing if we wanted to avoid this strong dependence on beta? That's what the problem we're trying to solve. Say again? Second base resistor. Would that help with the beta? No? I want something that actually takes this voltage and divides it across other things, right? So one way to do that is to basically introduce a resistor in the emitter. So if you take this thing, right, and you have VCC, now what happens is that this voltage is divided between this and that, but this is mostly carrying IC. I mean, it's IC plus IB. It's IE, but it's close to IC, right? It's IC over alpha. So what do you get in this case? Let's see. So this current, so this, what are the voltages? This is IB still, right? But this is IE, which I'm saying that roughly is close to IC. Right? It's to a factor of alpha. So if you start from here, you can say VCC minus RB IB, which is the voltage drop across this guy, right? Minus VBE on, which is the voltage here, okay? Minus REIC is 0. Right? So it's this voltage plus this voltage plus this voltage, which is VCC. Now, you can rewrite this as VCC minus VBE on divided by RB. Okay, now, so, and sorry, this is IB, which I can rewrite now as IC over beta. So then this will become RE plus RB over beta. So this, if you solve for IC, that's the expression you will get. Now, what do you see from this expression? Have we helped or hurt the dependence on beta by introducing the RE? And one way to check it is to set RE, by the way, to 0 to see that it will reduce to this guy. You will see that it goes back to the red one. Right? So, has it helped? It has helped, right? Because now, if beta fluctuates a lot, as long as this term is not insignificant compared to that term, you're attenuating some of those fluctuations. And in general, if your RB can be made small enough so that RB divided by beta is much smaller than RE, then you can basically get rid of the effect of this thing, and then you will have no beta dependence. So that's the direction we are going. Now, how do we generate this to make it more or less dependent on the fluctuations in RBs and also make it better defined? One way to do that is basically to make this voltage, the base voltage, out of two resistors, RB1 and RB2, and makes this very classic, old-fashioned implementation where you basically have an RE here, and then you have this thing. So now what you have here, so this is VCC. What you have here is this combination you can think about as and think about this and think about its Thevenin equivalent. The Thevenin equivalent of this thing would be a voltage source in series with a resistor. That resistor is the resistance you will see when you null all the independent sources inside, which is the only one is VCC. If you null the VCC inside it, what you see is RB1 parallel RB2. And what is the voltage that you will see when you draw no current? It's basically the division ratio times the VCC, RB2 divided by RB1 plus RB2 times VCC. So it's as if you've connected that here to the base, that equivalent, like that purple circuit. Now, or magenta, whatever that color is. Now, and then you can basically use this to have 2 degrees of freedom to play with setting this voltage as well as controlling this resistance. And by doing so, in conjunction with the RE, you can establish a relatively stable bias. So let's pick some numbers, right? Let's say we want to generate, let's say, 1 milliamp. So for 1 milliamp, let's say we want to drop about a volt here. So what should this resistor be for this to be 1 volt with 1 milliamp? 1 kilo ohm, right? So make this 1 kilo ohm. Now, and then if this is 1 kilo ohm and this is 1 milliamp, this is going to be 1 volt. What is this voltage going to be DC at that point, roughly? 1.7, right? 0.7 above. So this is going to be 1.7 volts. So I want to establish 1.7 volts. I don't know. Let's make this large. Let's say this is a discrete thing. So what do we have? What do we have here is 10 volts. So how should I select these resistors? Roughly, I can make this, let's say, 17 kilo ohms and 83 kilo ohms. This is something that you can basically make with components out of the stockroom, for example. Right? Close. Now, we have to check one thing. We have to make sure that the base current is not going to introduce too much of an error in this branch of the current. So what is this base current? If this is 1 milliamp of collector current, the base current, let's say beta is roughly 100, is going to be 10 microamps. If you draw 10 microamps out of 83 kilo ohms, how much voltage do you drop? So micro and kilo give you a milli. So you will get 830 millivolts, right? That can be significant. So you may want to actually reduce these. So instead of these, you may want to make, instead of making them 83 and 17, you make them 1.7 and 8.3 kilo ohms. So you were going through the process of how you pick these values, right? So now you have 10 microamps going through 8.3 kilo ohms, so you get 83 millivolts drop, which is tolerable. It's not going to significantly affect things. So that's a good set of numbers. And then what do you do next? So let's say you want to make an amplifier with this thing. How does this amplifier look like? Well, the other thing we need to choose is the value of the RC, right? How do we choose the value of RC? How would you choose it? Well,
to make sure the transistor is not insaturated.
so one thing, so there are multiple considerations, right? One is, as you pointed out, you have to make sure that the transistor remains in the forward active region. So from a DC perspective, you have to pick it so that that's right. But also from an AC perspective, you have to pick it so that it has sufficient gain. You're designing for you're trying to make an amplifier, right? So we need to make it such that it has gain. So we have to think about these multiple considerations. So let's talk about the DC part. So how would you choose the RC? What value of RC you choose, and how would you choose it? Let's say you're not worried about right now too much about the gain. Let's say we want to make sure that it has the maximum swing. By that, I mean the output can go as high and as low as possible. So basically, let's say this is 0, this is 10 volts. It can get very high to 10 volts, and it can swing as low as possible. So I want to get as large a voltage swing on the output as I can. How should we choose that? Give me some bad examples first. We don't say 0 and infinity, but tell me a resistor that's, give me a resistor that would pushes a transistor into saturation first. Pick something that pushes the transistor into saturation. Remember, according to this, the way we've designed this, the transistor is operating around, nominally is operating at 1 milliamp of current, right? So give me a resistor that pushes this transistor into saturation. 10K, yeah? So 1 milliamp times 10K means that if you're drawing 1 milliamp out of this guy, 10K, this is going to be 10 volts, so this has to be at 0 volts, which basically means that this voltage is low enough that would be saturating this guy. Because there's also voltage drop across here, there's a volt here, right? If you look at the DC voltages, right, nominally there's 1 volt here, and if you make this 10K, you will need to drop 10 volts, which basically means that you don't have enough, the transistor will saturate and none of these numbers will hold anymore. So 10K would be too high. What if I pick it to be 100 ohms? What happens? If RC was 100 ohms? What's the problem there? Low output resistance is 1, which may be a good thing or a bad thing, and then it will have impact on gain, for example. But that's correct. But from a DC swing perspective, what do you think will happen? So how much can it? How low would it? What voltage would it be operating normally at here? 9.9 volts, right? 100 millivolts below, because it's 1 milliamp times 100 ohm. So if this is 10 volts and this is 0, it's nominally staged here. So you can imagine that it will not support very large swings, because if the swing becomes a little bit larger than that, then it gets clipped, right? So you want to pick it where? Where do you want to ideally pick it? So you want to pick it so that it has enough room on both sides, right, to swing as much as it can. So can I pick this? What if I pick this at 5 volts? So let's say we center it at 5 volts. Would that be optimum? Okay, some of you are shaking your heads. Why is it not optimum? That's correct, but why not? Because the bottom is not at 0, right? The lowest this can go is determined by this voltage and this voltage. So even nominally here, this is at 1.2 volts, not 0. And now, when you try to go lower in voltage, you will drive more current, right? So you will drop more voltage here and more voltage there. So how do we choose where to put that? Well, there are different ways to think about it. So you can say, when you're carrying the maximum current, when you're at the lowest point of your swing, right? At that point, what should the transistor be? Where should the transistor be in terms of operation? At the edge of saturation, right? Because that's basically pushing it to the limit but not past the limit. So at the edge of saturation, this voltage is like 0.2 volts. And at that point, you're carrying the maximum current that would basically say whatever that IC max is, right, times RE plus Vsat, which is this 0.2 volts, has to provide the voltage here, which is VCC minus RC IC max. Right? Is it too small? Sorry. Let me write it. So this voltage, VCC minus RC IC max at that point, which is the voltage at this node, has to be equal to VC sat, let's call it V sat, plus RE times that IC max, or I max, let's call it. I max. Okay? So we can solve for I max, or we can solve for RC, one of the two. If I pick this to be, let's say IC max were 2 milliamps, right? At that point, this voltage would be what? If it's 2 milliamps, for maximum current would be 2 volts, right? So I have 2.2 volts, so how much do I have left? A little bit less than 8 volts. So I can put it actually, let's say, at 6 volts, and then I will have 4 volts up and 4 volts down. So if I do that, if I do it, for example, here, that way, and then make this IC max 2 milliamps, you will see that you get an RC that's close to 4 kilo ohms. So with 4 kilo ohms and 1 kilo ohm here, what you do, let me just write it in black, 4 kilo ohms, what you do is that you will produce, you start operating at 6 volts, you have 4 volts to go up and 4 volts to go down, because that leaves about 2 volts down here for this drop plus maybe a little bit of that. Now the exact value may be a little bit off from this. That's the ballpark of where this kind of biasing takes you. Again, this is a very discrete, very standard components like transistor level that you buy from, and resistor design and things like that. So let me ask you this question. What is the gain of this stage? Less than 4 or less, right? Because also you have the RM. Yeah, it's 4, because it's 4 kilo ohm divided by 1.025. So your gain is kind of almost fixed now. But is that true? Do you really need to be limited by this? What is making your gain small? What is the thing that has made the gain really small? The primary parameter, the primary component that has resulted in this gain being small. What is it? Well, RC, yes, but it's really someone else. This guy, right? If I take this and make it 0, what would my gain be? Just let's forget about biasing issues. What would the gain be if that were 0? It would be 4 kilo ohm divided by 25 ohms, right? As opposed to 4 kilo ohms divided by 1 kilo ohm plus 25 ohms. The RM, right? Or GM. So that resistor is really killing your gain. So is there a way to have your cake and eat it too? In the sense that you put that resistor there to make the biasing stable, right? But it's only there for biasing. It doesn't have to be really there for your signal. It's only there for DC. Can you separate the DC and AC? Yes. For the capacitor, right? Bypass, right? So one of the things you could do, you can say, look, I'm going to put a big fat capacitor here and just basically bypass that. Just create a short. So at AC, you basically create a short. At anything that changes, you connect it to ground. So from an AC perspective, what is the gain now? From an AC perspective, if this capacitor was large enough, RC over RM, right? Or GMRC. So what is that gain? What is that number? For 1 milliamp that we bias that? It's 25 or 40 millisiemens times 4 kilo ohms. You get 160, right? Roughly. So you can get a gain of 160, but at the same time, you have made the bias stable there. Now, the other question is that how do you get the input and output to this thing, right? So you need to, if you were to bias this, again, this is discrete biasing. This is very classic, and we'll talk about integrated biasing. We already have kind of, but we'll continue to talk about it. There is a source resistance, right? You cannot just connect it directly here because the DC of the source will mess it up. So that's why you need to have another decoupling capacitor here in general. And the output, the same thing. So you put a capacitor here to your load. So this is a very, very classic amplifier stage. Now, but the interesting thing about this thing is that by biasing it this way, we've effectively made it, and if you choose the values such that you have the proper relationship, you have effectively made it less dependent on the specific of the transistor. You don't see the exponential there anymore, right? In the biasing, you don't even see the exponential much in the gain characteristic if you don't have the bypass capacitor. So essentially, this biasing technique makes it less dependent on the specifics of the transistor, which basically means that you can take this transistor out and replace it with a different kind of transistor. And these kind of biasing networks become less sensitive to it. So you can take it out and put a MOSFET there. And yeah, it will change a little bit. And then you can take it out and put a vacuum tube there. Again, it will change a little bit. But it's not going to be fundamentally different from something like this, which was strongly dependent, or even this, which was strongly dependent on the specific parameters of the transistors. So that's really the first step to making your biasing network more stable. And we'll take multiple steps over time. As we go later on, we'll see that there are much more sophisticated ways of generating these currents and voltages to make the gain independent of temperature and voltages and things of that sort. That will evolve out of this thing. But this is a very basic, classic, low frequency, or like a discrete amplifier. Now, in integrated circuits, you don't see these kind of bypass capacitors as much. Why? Because first of all, they're big and expensive. Second is that these kind of capacitors will limit your low frequency cutoff of the system, meaning that very low frequency stuff doesn't go through it unless you make this gigantic. So you will not only have a high frequency limit, but you also have a low frequency limit, which we'll learn how to calculate later on. So instead, you go to stages like the differential amplifier that allow you to cascade without having to be DC coupled. So you can have, for example, an amplifier stage let's make it a fully differential one. And then you can take it to the next level. So this is biased with a current source that would go to the next stage of amplification. And you can repeat these things without having to worry too much about a coupling. And this allows you to create a DC coupled system. This is an artifact of the fact that capacitors are expensive, transistors are cheap on integrated circuits. So what you may implement like that, which looks very different from this differential amplifier on the surface, is essentially the same thing. These are two manifestations, very different looking manifestations of common emitter. This is how a common emitter will look like in a discrete circuit. An example of how it will look like. And this is an example of a common emitter or common source or common terminal 1 in an integrated setting. But since you understand the underlying principles, you can get past this like seemingly very different surface and get to the crux of it, which is that these things are essentially based on the same fundamental stage. Does it make sense? And we will develop more and more of these biasing techniques as we go, and we'll make them better and better as we go through the process. So by the end, we'll be able to replace all of these little non-ideal elements with things that are based on transistors and make them work. Okay, any questions?